Thank you, and hello, everybody. The title of the talk is the sparse decomposition of dynamical systems. Yes, this doesn't sound too much like polynomial optimization, and unfortunately, I won't address this too much in this talk, but at least this common theme of sparsity here appears. Polynomial optimization describes the beginning of the story that led to that talk, because with Milan, we worked on a project where we used polynomial optimization for dynamical systems, but it had the problem that it scaled badly in the dimension of the dynamical system. So we had to search for some possibilities to reduce the dimension, and we came across the sparsity concept. But to be fair, and we realized we used it, but then we also realized this does not only apply to polynomial optimization techniques, but in general. So this is where I arrived here, and this is where I want to present this sparse decomposition technique for general applications to dynamic systems. So to what kind of systems do we want to apply this? Here. So here are some examples. Okay. Some less sparse examples like here, or some examples that we came across in this workshop already, like power grid systems that have admittably a sparse structure. As you can see here, there's some branchings taking place, and the energy is distributed maybe here from the center towards some outside districts, and it's really branching out. And this is a structure that in our case is beneficial. Other examples are like this network here, which is a social network where we have separate subgraphs. We also have branching structures here, very independent nodes, and something that doesn't look so sparse. So in the more modern term of some sparsity structures here are bubbles, but also systems where some sparsity appears are these protein-protein interaction networks. I don't have much information. I don't know much about this, but at least when looking at the graph here, it really looks like there is structure that can be exploited. And also there are some cherries here. We'll encounter them later. So what's the rough idea? So we want to consider a problem with underlying graph structure. So in that case, that will be mostly a dynamical system. But for those of you that are not so familiar with dynamical systems, you can choose your favorite graph problem. For instance, optimizing a power flow, or the traveling salesman problem, minimal calling number, and so on. Because I think the idea we use here, you can easily encounter in your favorite graph problem as well, just to illustrate what our method does for our case. I think you find similarities to your chosen problem. What we want to do, we want to exploit underlying structure and like underlying graph structure. And this is, in our case, this is a very easy structure. Namely, we look for independent subgraphs, and we use these subgraphs, or the idea is to use these subgraphs to decompose the whole problem into the smaller problems, or into the problems on the subgraphs, allowing to get in the end a solution of the whole problem. So what could be examples for this? For example, if we have a graph that just consists of disjoint unions of the union of disjoint or disconnected subgraphs. So then, for example, if you're interested in the minimal coloring number of this whole graph, then of course you can just color all the subgraphs and then take the maximum of the minimal coloring number. Similarly, for shortest paths, for example, in here, if you want to find the shortest path from here to here, and since there's only one node, one edge in between here, the shortest path is exactly the shortest path from here connecting these two nodes, then taking the only one option here, and then finding the shortest path from here to here. And here, this social network that we've seen before, I guess for every graph problem you've chosen, you can find some structures here that can be beneficial and exploited for your problem. Okay, to be a bit more precise about our setting, this is the following. We look at dynamical systems. So that means, and in our case, in continuous time. That means we look at the differential, an ordinary differential equation x dot is f of x with the initial value x0. Our vector field f consists of the components f1 to fn, and the solution map we denote by phi. That phi here, that just means this value here is the solution to that differential equation at time t using the initial value x0. And finally, we need some notion of a projection that we'll use. So for an index set or set of indices I, we denote the projection onto the components, the canonical components indexed by phi I, and similar for vector fields f and the flow. So by fi, we just denote the components of our vector field indexed by I. And by ti is the flow of the corresponding subsystem induced, or of the ordinary differential equation induced by this function. And having this notation, we can define what we would call a subsystem. This will be the main object in our talk. So a pair of an index set and the corresponding component functions of the vector field is called a subsystem. If the states, if the component functions fi depend only on the states that are indexed by I. Another equivalent definition is the following. That means the stat here that says that the projection onto the coordinates of I intertwines the vector field, the smaller vector field with the whole vector field, and similarly for the flow. And for these three equivalent statements, I think this can be reformulated in a different way. So the first part here, this here, is something that is easy to check. You just need to check if our functions fi depend only on the states xi or not. The second one is a bit easier to interpret, because that means that the dynamics of the states xi, so this is that side here, is independent of the other states. So that is what this side of the equation says. And the last statement here is something that is easy to use, because it says, it gives us information about how the subsystem behaves. Namely, we get solutions for the subsystem just by projecting down from the whole system. And this will also allow us to go back. Even if we have solutions here, then what we need to do to find solutions here, we try to embed, to reverse this projection. So to give an example, let's look at this dynamical system here. How can we display a subsystem? So first of all, what we do to illustrate this, we make nodes for a graph for each of the states. And in the second step, we here's something a bit rough happening. We totally forget about the exact relations here. We just note, aha, okay, the first one, x1 dot really depends on x1. The x2 dot only depends on x1 and x2, and similar here for the others. But we forget about how this exact relation looks like. So this is a bit rough here, but we just look at this correlation sparsity for this concept. And what we do next is when we have say reduced our system just this easier setting, we'll illustrate dependencies of different states by arrows. So if we look at x1, then we say x1 only we see x1 only depends on the dynamics of x1 only depend on x1 itself. So we indicate this by drawing an arrow from x1 to itself. But self circles we just omit. This makes the graph a bit easier. But for x2, something different happens. So for x2, the dynamics, we see that it depends on x1. That means we draw an edge from x1 to x2. So such an edge means x2 depends on x1. And similarly for x3, we see x3 depends on x1. So there should be an edge here. And it also depends on x4. So there should be an edge here. And this is exactly what happens. And if we continue this, we get a graph that looks like this. And this is what we call the sparsity graph of our function. And this will be the main object we'll use to identify subsystems. But we didn't talk about how they can be used. But before doing this, I'd like to give a short example how we can identify subsystems using this sparsity graph. So here, the colored things, they always denote subsystems. As a small reminder, here is the definition again of a subsystem. But what it says is that if we only look at the colored nodes together, then we see that their dynamics is independent of the rest. So for example, for x1, this is trivial. We just look at the node x1, then we don't have a need to include other nodes into the dynamics. Let's look at a bit more less trivial example. For example, here. That means we only look at those three nodes and look how they behave. And we see the dynamics of x1 depends only on x1, so we don't have need for x2 and x5. And for x3 and x4, it's the same case. So we don't have need to include these other two states. Okay, these are some examples. Now, how do we use subsystems? So the main idea is using this third equivalent relation, we can say that this diagram here commutes. And this allows us to transfer properties from the whole system to properties from the subsystem, namely exactly by projecting when we want to have properties of the subsystem. And we can also obtain properties of the whole system by embedding properties of the subsystem and also then gluing them together if necessary. So this concept I'll explain a bit later as well. But this is the main idea here. And to be illustrated down here. So we have our whole system. In that case, we find two smaller subsystems here. And the idea is using these two small subsystems or smaller subsystems, we also want to find properties of the whole system. And this is exactly what Milan and me used in our first version, where we actually applied the polynomial optimization, with the idea that we want to solve something down here because we have less variables. We don't need the variable x3, only the colored ones here. We solve a similar problem here for this subsystem of those yellow nodes, and then we try to go back and glue them together. This is what like gluing meant here to obtain an object for the whole system. So our main theorem informally reads like this. So if we have some minimal regularity assumptions on F and several subsystems, then there are some good things that hold. This is a bit long. You don't need to pay too much attention to what is written here. I think the main message is that many objects from dynamical system decompose according to subsystems. So, for example, the first one is trivial. If you have an equilibrium point, then this is clearly also an equilibrium point of the subsystem. And even using this assumption here that says we have enough information only from the subsystems, we can also say if such a point is an equilibrium point for all the subsystems, then we already know it has to be an equilibrium point for the whole system as well. Something similar holds for invariant sets. And only in point 3 there happens something that is a bit more interesting, namely this gluing procedure. So if we have sets, in that case, what we call invariant, or some certain sets that have good properties for a subsystem, we want to obtain a set with the corresponding property for the whole system, and this is done by gluing them together. That's what we call it, this is stated here. So why did we call it gluing? So typically it's the case that those subsystems, they nodes, they overlap. That means, so the underlying idea is if I have sets for the subsystems and I want to create a global set for the whole system, I have to take into account that the subsystems, they coincide on some nodes. So what that means, in order to create a global set, also the global sets have to coincide on this overlapping, and so we glue it together on this overlap.
But the glue could be empty.
Yes, this is something that is particularly important for applications when we try to approximate the object for the subsystems. Then it can happen that if the approximation is not precise enough, that the glue really ends up empty. But as long as for example, as long as we know that an invariant set of the whole subsystem exists, then this guarantees us that this gluing procedure is non-empty as long as we look for the right object. But you're totally right. This can be empty. But as long as you search for the right object, then the existence of that object for the whole system guarantees that I can find objects in the subsystems such that the gluing procedure gives us the object I want, but it won't be empty. Okay. Yeah. And the very informal.
I'm trying to say about so for instance, if you have, so would it be that you could have some stable and unstable manifold and they glue together to give something interesting?
Well, this is an interesting question about mixing objects. I'm not so sure. I think this is interesting, but what I think the general philosophy that I followed here was I looked for an object that I'm interested in for the whole system, and I tried to decompose it into the corresponding object for the subsystems. So mixing objects seems interesting, but I'm having a hard time, I think, to imagine what that object.
Imagine that a region of diffraction is a mix of stable and unstable.
Yes, but I was mostly looking at I looked at the definition of the region of diffraction. Okay, but I definitely find this is interesting. I think I'll look into this. Okay. But, so for those of you who are not so familiar with the objects that were just listed before, so this is the very informal statement of the theorem. So many intrinsic objects of dynamical systems are decomposed into their counterparts of the subsystem. This is really just due to that a subsystem is a very intrinsic object if they exist. Okay. And to give an example of how such a procedure works, I want to talk about Lyapunov functions and asymptotically stable equilibrium points. So to recap the definition, so an equilibrium point is a point where the dynamical system stands still. So that means F, the vector field, vanishes at that point, and it's called asymptotically stable if all trajectories are attracted by that point. So they shrink together to that point when time goes to infinity. And a Lyapunov function is non-negative, here say one function, such that this gradient here is negative. So that means the V typically represents the energy, and that means energy is decaying in time. Now we'll use this following theorem by Lyapunov. It says that X is asymptotically stable if and only if there exists a C1 Lyapunov function for X. So that's a very intimate connection. And using this, we want to see that an equilibrium point is asymptotically stable if and only if it's stable for all the subsystems. Let's take any subsystem. First, let's check that if we project that point, this is an equilibrium point for the subsystem. This is exactly stated here. And convergence to that point just follows from continuity of the projection and the property that solutions of the subsystem are exactly projections of solutions for the whole system. And using asymptotic stability for the whole system gives asymptotic stability of the subsystem. To reverse the statement, we assume that projections of that point X star are asymptotically stable equilibrium points for all the subsystems. So using Lyapunov's theorem, we can find Lyapunov functions for the subsystems. And then in that case, doing them together is easier. We just need to, we want to define a Lyapunov function for the whole system, and we just do this by embedding a function, a Lyapunov function of the subsystem, to a function acting on the whole system by composing it with the projection, and then we just sum them together, and we see that this gives Lyapunov function for the whole system. And then applying again Lyapunov's theorem, we see that since we have a Lyapunov function, we know that the point we started with has to be asymptotically stable for the whole system. Yeah.
Only one half of the theorem is due to Lyapunov, right? The existence of the C1 Lyapunov function.
Okay. Oops.
Like 1950.
Okay. Yes. Sorry. Yeah. So that shows some interplay between the subsystems and the whole system. So so that might also lead to the question if subsystems are just correlation sparsity. And here I would say yes and no. This depends on the notion of correlation sparsity. When I started to work with Milan on the sparsity patterns, we were using polynomial optimization, and there at the beginning it looked like it. We used the correlation sparsity of the polynomial optimization problem, but then it looked like in fact we don't so much, and I would say that's you that it's not exactly the same as correlation sparsity we encounter in for polynomial optimization problems, but it's still a correlation sparsity, but just in another sense. So to give an example, so suppose we look at this cherry structure dynamical system. Why cherry? Because the sparsity graph looks like this. So that means the dynamical system is of this form. This is the easiest example of a dynamical system that has some correlation sparsity, or that has some subsystems. And when we want to check asymptotic stability of the of an equilibrium point, then a typical ansatz is to search for Lyapunov functions, as we've just seen, and this can be done by sum of squares methods, or at least you can try. So how does the problem at hand look like? We look for a polynomial that is a Lyapunov function. That means it's non-negative, so we present this by being a sum of squares. it should vanish in our equilibrium point, and the gradient should be negative. So the gradient times f should be negative. So that means if we take minus that thing, it should be sum of squares as well. And if we look at this problem now, we see that there is sparse structure in F, but it's not a priori clear that we can also assume sparse structure in P. Because here, for now, it just looks like this polynomial is it can be any polynomial. It does not necessarily have to be sparse.
Corby, that's
Yes.
Didier. Can you hear me?
Yes, hi.
Yeah, it should be a little bit careful because P equals 0 always works. So
Yes,
there should be some strict positivity and so on.
Yes, yeah. If we should add some more conditions, maybe that it grows quadratically, for example. This is due to that the more specific P is, the better information we get. So if we take P is 0, then this is definitely feasible, but we don't get so much information out of it. Thank you, Didier. So there should be we should add some more conditions here. But my main message that I wanted to show is that we don't have a priori sparsity on P. And yes, applying our result, you could argue that you can enforce a priori sparsity, but we also do this, but just in a different way. Namely, we solved this Lyapunov problem for the two subsystems separately instead of solving it for the whole subsystem. So instead of solving it on the variables x1 to x3, we solve it on the variables x1 and x2 and x1 and x3. So we've reduced the dimension. So to sum it up, I would say even if we apply sum of squares methods, we use rather the sparsity structure of the dynamical system itself than the sparsity we could encounter of the sum of squares problem. But using the right formulation, I think we can make them coincide. But to me, the moral is that we use sparsity of the dynamical system. So it remains to address how we can find subsystems. And there, again, the sparsity graph comes into play. We use the sparsity graph because it's an easy and discrete representation of the correlation that we have. And now, if we would have a graph theoretical representation of what it means to be a subsystem, we could apply purely discrete methods. So let's see how something like this could look like. So if we were interested in what subsystem could look like that contains x5, what does it mean? So we know that the dynamics of x5 depend on x2 and x4. So that means any subsystem containing x5 has necessarily to contain these two nodes or these two states as well. And for these, we see, okay, they depend on x1. That means necessarily a subsystem has to contain x1 itself. But in x1, this chain ends. We are not forced to include another node like this node x3 here, because there's no x1 does not depend on some other states. Otherwise, there would be an arrow pointing towards x1. So that is what leads us to the definition of the path of a node. The following. We define the path of a node to be all the states that eventually influence another state. So the path of that node x5 are exactly those four nodes, because indirectly they influence the state x5, because x1 has influence on x2 and x2 then influences x5. So then for a graph theoretical notion, that means an element is in the path of a node if there exists a path in our direct sparsity graph from the node in the past towards the element that we are considering. And having this, we can characterize subsystems just by looking at the graph, namely a subsystem indexed by I, or is a subsystem if and only if the past of each node is contained in the system. But that really just comes from that the past determines all the nodes that influence eventually the dynamics of a state. And using this, we're almost done. The last step that remains, to be clear, is talking about circles. This is the last step we need in order to give an easy algorithm for finding subsystems, because circles are something bad for our case. This is stated in the following lemma. If we have a circle in our sparsity graph, and if we look at any subsystem that contains one of the nodes in a circle, then necessarily the whole circle has to be contained in a subsystem. Yes, a loop. Yeah. But this is also very clear. But because if you have a circle, then that means each node influences any other node as well. So to say, for those of you that like discrete graph problems, that would induce a complete graph, for example. And that allows us to simplify in the following way. Is there a question?
Comment.
Sorry.
Yes?
Yeah, I have the same question as Monique actually. So she says a circle is a directed circuit.
By a circle, I mean a closed loop in the directed graph.
Okay, so it's not like a cycle.
Oh, I mean cycle. Sorry.
Okay.
Sorry. Circle means cycle. I often confuse this.
Sorry.
Yes. Okay. So directed circuit. Okay. Sorry. So okay. To fully clear what I want to say is so we can detect circuits, circles, or cycles here. So we have here a loop or a path that starts and ends in the same node. Here, for example, and similarly here. How do we have to walk here? We start here, go there, and then we end up here. Yep. Yeah. So as we've seen that circles, they always, or the elements in a circle, they always appear together. What we do is we just we contract them. That means we just take the whole circle and represent it by one of the nodes in the circle. So this is called a vertex contraction, and it leads to the following. So if we've done this with all circles, we end up with a directed graph with no circles. So this can also be called a forest. And with that graph, we can easily work. And I want to show this in the following example. So suppose this is our sparsity graph of the dynamic system we have at hand. So it does not always need to be very easy. First thing we do is we look for circles. They're here. Once we found the circles, we contract them. So each of the colored nodes here will become one single node in that color. So this is done here. And now we have a forest. And what we need to do now is we need to detect the leaves in the forest. These are here. And based on the leaves, we can easily find subsystems, namely by considering the past of that leaf. Yeah. So for each leaf here, we've colored the past of that leaf. And what the property now is that if I combine them, overlap all of these, we would see that every node is covered. So every node in here of the full graph is contained at least in one of those subsystems. Yeah. So this is exactly what we needed for the main theorem that is stated. So this presents an easy way of finding a covering by subsystems that provides all that is necessary for us. Yeah. And then the idea is, instead of solving the whole problem here, we just want to look at those smaller problems on the subsystem. Here, yellow one, and also the blue one, which unfortunately looks a bit huge, but yes, we cannot also solve it. But there are also problems. So if we look at the same graph from before, what easily happens, for example, if there is a connection here between these nodes, then that means this is turned into one full circle. And circles, as we have seen, they are bad because we cannot reduce. We should look at other techniques as well. Especially, for example, if this connection here if it's only small, it can be very slight interconnection of dead nodes. It really disturbs our correlation sparsity a lot. So correlation sparsity shouldn't be the only thing that we should look at. Other possibilities could be to exploit term sparsity. We've tried this with Victor and G1. He did a lot of work there, and we just seemed promising as well. Another concept that is complementary to sparsity is symmetry, and this shouldn't be mistaken with symmetry in the sparsity graph. It's really symmetry really also takes into account how the interconnection here looks like. So when talking about symmetry, we cannot just forget how the interconnecting edge affects the system quantitatively. But at the same time, I think our approach still motivates a bit refined approach to sparsifying dynamical systems. So what often was done was when they had a dynamical system and they looked at the at how the nodes are connected, people like to just cut some nodes and say, okay, now I consider the dynamic system consisting of one dynamic system only consisting of x1 and x3, and a separate one consisting only on x2. But I think we motivated that it's not always best to do this, but rather maybe considering the two dynamic systems with having some overlap. Yeah, and starting from there, we can also apply further reduction techniques like symmetry or term sparsity, or having this idea in mind when cutting edges in the sparsity graph. That is also okay to have some overlap. This already exists, but I think we also motivated it a bit further. And talking about cutting edges, I want to point out that sometimes it's important to not forget about edges that are very important, and especially one instance, cutting edge one. For example, when real algebraic geometry joins optimization. And by that, I want to conclude my talk. Thank you for your attention, and if you have questions, I'll try to answer.
Thank you. So do we have a question? Here or there? Yes. Thank you, Kobe. That's the first talk. So with regards to like these, you mentioned that if you have this connecting agent, you create a big cycle, and it's pretty bad for your sparsification process.
Yeah.
So I was wondering, like, can you quantify how bad it is, or like, I can see from the modeling point of view, and maybe time-wise will take longer, but like solution-wise, let's say you do let's say in your model you have a very weak edge between two really big clusters. Can you disregard it and still get a decent answer?
Yes. This is a very good point, and this is what I wanted to address here when I was talking about this. So often people, when they had something like this, and say, so this is a very important approach. So, for example, if, as you said, if that edge is just gives a very small interconnection. But since when we talk about the sparsity graph, we totally forgot about how strong this connection is. We just see there is one. But if this connection is just small, it would be good to forget about it while introducing a small error. And at the same time, guaranteeing that I don't have to merge all those nodes together. So there are approaches that look at which edges can I cut, so that I introduce just a small error. And this is a very important point. For example, if you look back at the motivating examples of systems here, then there might be some sparse structures, but typically they are still too large, and you have to reduce further by cutting some edges. And the edges that you want to cut are the ones with the least influence.
Okay, so do you have like a quantitative bound on like the cut versus the uncut? Like how big can your difference in solution quality be?
Yeah, there are rough estimates, but they're often too coarse. So they're working on different techniques on estimating somehow how large the impact is of reducing one edge. But I think for the moment this is mostly restricted to large linear systems because it's different. It's difficult analysis. But this is a very good and important point. Thanks.
You other questions here?
Yes. Can I ask? Yeah, it's Didier.
Yes.
Hi, Kirby. Thanks for the nice talk. So within the PhD thesis of Matteo Tacchi, we observed that for the region of attraction problem, we observed that even though the system is sparse, it may be that the region of attraction itself is not sparse. And so we can approximate the region of attraction using sparsity, but usually this cannot be done with convergence guarantee, since the object that we are approximating does not have this structure. So let me return to the discussion with Evelyn on this gluing. So what kind of statements can you make about for example, region of attraction or invariance set, about the fact that the object you want to compute is actually can be constructed by gluing, or maybe by taking unions of gluings, or what kind of statements can you make to ensure convergence while exploiting sparsity for this kind of computations?
Yeah. First, maybe to relate to Matteo's work, I think Matteo's work is very good to motivate what we're doing, but also it drastically shows where our approach is not working, because Matteo's I don't know if I have a slide that could show Matteo's setting. So in Matteo's setting, the sparsity graph is just a line connecting one node to the next one. So this really looks sparse, but and you would very much expect that there is some sparse structure. And Matteo looked into this, and he found cool things. But our method does not help in his case, because the systems we would have to look at is the whole system itself. So our method does not apply to Matteo's settings. So from my perspective, I would say that makes it a very interesting problem what Matteo is considering. But it also says that even though it looks like there's lots of sparse structure, our approach does not capture this. And yeah, I think I have to give a similar answer than to Evelyn's question. So this might not be so satisfying, but the idea is that we want to show for the dynamic system that it already has intrinsically this decoupling nature. So the problem, if we look at the region of attraction, for example, and we have a sparse system, then we argue that the region of attraction already decouples into the corresponding object of the subsystem.
Okay.
So this is an intrinsic problem structure of the dynamical system.
So you assume that the object you want to compute is sparse?
notice this follows from the sparsity of the dynamical system. So I think the theorem in that sense would repeat. If you have sparse structures of the dynamic system, like subsystems, then you know that the region of interaction decomposes into the splued versions of the region of interaction for the subsystem. It's a consequence of sparsity structures of the dynamical system.
Okay, so you identify a certain notion of sparsity, which is such that the objects you want to compute decompose.
Yes, exactly.
I see. That makes sense, yes. And you're saying that what Matteo did does not fit this framework.
No, it's too hard. It's too hard for us.
Okay. Many thanks, Kirby.
Yeah, thank you.
So in this case, you have only one subsystem.
Yeah, the whole.
So,
okay, there are also smaller subsystems, but the important one is only the whole system itself.
Yeah. So if you cannot split, there's no gain.
Yeah.
Hey, may I follow up on this discussion maybe? So it's Matteo. So to summarize maybe, so the thing is you identify a subsystem, which by basically saying that a subsystem is a system where no arrow enters.
Mm-hmm.
Which means that the variables of your subsystem absolutely don't depend on the other variables of the whole system.
Yeah, exactly.
And this allows the decoupling because since all the dependencies are within the subsystem, then it makes sense that to look at this subsystem as an isolated system, right? It doesn't depend on the rest. So that's the reason why you have this sparsity in the regions of attraction, for example. It's because, yeah, you have no influence of external variables on your systems. So it makes quite a lot. Well, it makes sense, and it seems to be quite optimal for decoupling because you're really taking the biggest. Your subsystems are the biggest parts of your graph that have this property. So I think one could not do better. By ensuring that there is no dependence on other variables than on your subsystem. And so I would like to ask you if you think that it is the limit, or if you think that we could, even though there are, if we could consider more generic correlative sparsity structures where you allow influences external from your subsystem, but still get convergence guarantees. That's quite challenging.
Yeah, I think from an aesthetical point of view, I would assume that this is the limit because as soon as you allow something more, you lose. Or is it you lose that this diagram here computes, exactly. And this was really at the base of what we were doing.
Yeah, your region of attraction won't be sparse anymore. If you take more generic correlative sparsity patterns than the one you are considering here, then you are sure that your region of attraction won't be sparse anymore. And the question is, okay, it won't be sparse, but would it be possible to approximate it as closely as desired with sparse objects?
I think this relates a bit to what Andres asked. If we neglect some edges, that then gives some smart structures. How much is the error that we introduce? Maybe.
Yeah.
I'm a bit torn. I would say when I look at your example, it feels like there should be sparsity that is sparsity at hand, but also you show that it doesn't look like there is too much sparsity still. So I haven't decided which if I'm in the optimistic or the pessimistic team. But I would be optimistic about exploiting term sparsity or symmetry,
yes.
For example.
Yeah.
I think this could go well hand in hand.
Yeah, term sparsity is also proved to converge, so that's the priority. But yeah, okay. Okay, thanks.
Term sparsity work. You've done that, right?
Yeah, but it's not so. I mean, it's in general, it's not so clear how great the advantages. I mean,
Yeah, you don't know how much you save.
Yeah.
But you know that you are
Yeah.
going to verify the sparsity
Yeah.
graph analysis.
Thank you. Do we have other question?
May I ask a quick question?
Yes, of course.
Yes.
Hello, Monique.
Thanks a lot for the nice talk. In your, probably you said it, but I just missed it then. In your main theorem, you had a very long theorem. And yes, and then you, no, yeah. And then you had this condition that the subsystems should be compatible to be defined.
Yeah.
So can you remind us what do you mean with the subsystems compatible?
Yeah. They have to be compatible with some constraint set X here. I skipped this because this, I think, would have made it just a bit more technical. And this constraint set X here arises from applications when you want that your dynamic system just lives on a certain subset of Rn. So you want to restrict it to, for example, the unit ball because it comes from some physical constraints, for example. Then that the subsystems they should be compatible. The sparsity should be compatible with dynamics, but also with the set you're considering. So that your dynamical system factors into subsystems. You also want that is true for your constraint set. So what you would like to have is that the constraint set X here is some product space.
So you want probably that your X is products of its projections, correct?
Yes, exactly. That's it. Exactly. Yes. Yeah.
Okay. So that you can go back from from the projections to the original sets.
Yes, exactly. Yeah. So I said X could be a ball, but a ball, if you take the Euclidean norm, would be a very bad example because it's not a factor of its projections. But the hypercube, for example,
fits.
Yeah. So also helpful in our case.
Okay.
Thank you, Monique.
Thank you.